All right, welcome to the Explainer. Today, we're going to talk about matrices. You've probably seen them, these big, intimidating blocks of numbers that show up in math and computer science. But here's the secret. They're not nearly as scary as they look. They're actually just a really smart, really powerful way to organize information. So let's dive in and break them down.
I want to start with a super simple question. Just for a second, forget all the complicated math stuff. Just think about this. What would you call a simple rectangular grid of numbers all arranged neatly?
Yep, you got it. It's called a matrix. And that's really it. At its heart, a matrix is just a grid of numbers all lined up in rows and columns, usually with some brackets around it. That simple idea, right there, is the foundation for everything else we're about to cover.
So, to really get a handle on them, we got to look under the hood. Let's get familiar with their basic anatomy, the building blocks that make up every single matrix.
Okay, so every matrix is made of a few key parts. See the horizontal lines? Those are its rows. And the vertical lines? Those are its columns. If a matrix has m rows and n columns, we say its size, or its order, is m by n. And each number inside, that's an element. We can find any element just by its address, its row and column number.
You know, not all matrices are created equal. Just like in the animal kingdom, they can be classified into different types based on their shape and what's inside them. Think of this as our quick field guide to the matrix family.
Let's start with the simplest ones. You've got your row matrix, which, you guessed it, is just a single row of numbers. And then you've got its cousin, the column matrix, which is just a single column. They're pretty much exactly what they sound like.
Next up, we classify them by their overall shape. If a matrix has the same number of rows and columns, we call it a square matrix. If those numbers are different, it's a rectangular matrix. And trust me, this little difference is a huge deal. It's going to determine all the cool stuff we can do with them later.
Now, inside that square matrix group, there are a few special members. A diagonal matrix is one where numbers only exist on the main diagonal line. Everything else is zero. If all those diagonal numbers happen to be the same, we call it a scalar matrix. And then there's the superstar, the identity matrix, where the diagonal is all ones. This guy acts just like the number 1 in regular math. And of course, there's the zero matrix, which is just full of zeros. Pretty straightforward.
All right, so we've met the players. Now let's see them in action. We're going to start with the most basic, most intuitive things you can do with them: addition, subtraction, and scaling.
The rule here is incredibly simple. You'll love it. To add or subtract two matrices, they absolutely must be the exact same size. You can't add a little 2x3 matrix to a big 4x4. But if they do match, you just combine the numbers that are in the same spot. Top left adds to top left, bottom right adds to bottom right. You get the idea. It's that easy.
Okay, scalar multiplication sounds all technical and fancy, doesn't it? Well, it just means scaling the matrix. You take one single number, that's the scalar, and you multiply every single element inside the matrix by that number. It's like a volume knob for the whole thing. If you multiply a matrix by 2, every number inside just gets twice as big.
And now, for the big one, matrix multiplication. This is where matrices really start to show off their power. But I gotta warn you, the process isn't quite as simple as addition. It's got one golden rule that you can never ever break. This is it, the golden rule. To multiply two matrices, the number of columns in the first one has to be the exact same as the number of rows in the second one. So you can multiply an m by n matrix with an n by p matrix. See how the two inside ends match? They kind of cancel each other out, and your new matrix will have the size of the two outside numbers, m by p.
So how does this actually work? Well, to get the very first element of your new matrix, the one in the top left corner, you take the first row from the first matrix and the first column from the second. Then you multiply the matching elements, so 1 times 5 and 2 times 7, and you add those two results together. It sounds a little weird, but this exact operation is how a video game takes a 3D model and spins it around on your screen.
And here we have the final result. That first element is 19. To get the next number in that top row, you do the same thing, but with the first row and the second column. You keep doing this little row by column dance for every single spot in the new matrix until it's all filled out.
Now, matrix multiplication shares some rules with regular math. It's associative and distributive. But here is the single most important thing to remember. It is not commutative. In normal math, 5 times 3 is the same as 3 times 5. With matrices, no way. A times B is almost never the same as B times A. The order you multiply in is absolutely critical. It's a one-way street.
Okay, so beyond the basic math, we can also do what are called transformations. These are things we can do to a single matrix to change it in some really useful ways. And the most fundamental one is called the transpose.
The transpose, which we write as A with a little t, is a beautifully simple idea. You're basically just flipping the matrix along its main diagonal. The rows become the new columns, and the columns become the new rows. That's it.
Check this out. See the first row of matrix A? It's 1, 2, 3. In the transposed version, poof, that row is now the first column. The second row, 4, 5, 6, becomes the second column. And just like that, a 2 by 3 matrix has turned into a 3 by 2.
So why do we care? Why bother flipping a matrix? Because the transpose can reveal the hidden inner structure of the matrix. For certain special square matrices, called symmetric matrices, transposing them does absolutely nothing. They look exactly the same. And that property is incredibly important in fields like physics and data science for understanding relationships between things. So when you boil it all down, what's the big takeaway here? Matrices are so much more than just a complicated way to do arithmetic. They are a language, a really powerful structured language for representing data and describing incredibly complex systems, from a network of friends to the pixels on your screen.
So we've gone through the whole thing. From the basic building blocks to the math and transformations, you now know the rules of the game. You have the basic grammar for this powerful language. So the real question is,